In the history of science, there are moments that redefine the boundary between the known and the unknown. There are days when a single piece of data appears on a screen and forces us to confront the humbling fact that the universe is far stranger than we have ever imagined. In 2015, such a day arrived. Astronomers, sifting through a flood of data from a space telescope, saw something that made no sense. A star, perfectly normal in every other way, was behaving as if a colossal, misshapen object was passing in front of it. Blocking out its light in a way they had never seen before, it wasn't just a dip in brightness. It was a plunge, and it followed no recognizable pattern. It was the day astronomers saw something they thought was truly impossible. To understand the impossibility of this event, you first need to understand the mission that found it. NASA's Kepler Space Telescope was one of the most successful scientific instruments ever built. Its mission was simple, yet profound: to find planets orbiting other stars. To do this, Kepler stared relentlessly at a single patch of sky containing over 150,000 stars, waiting for a telltale sign of a planet. This sign is called a transit. The principle is straightforward. If a planet's orbit happens to be aligned just right from our perspective, it will periodically pass directly in front of its star. When it does, it blocks a tiny amount of the star's light, causing a brief, subtle dip in its brightness. These transit signals are the fingerprints of an exoplanet, and they have three key characteristics. First, the dips are tiny. A planet the size of Jupiter, the largest in our solar system, passing in front of a sun-like star would block only about 1% of its light. For an Earth-sized planet, it's less than 1/100%. Second, the dips are regular. If a planet takes 30 days to orbit its star, you will see a dip every 30 days, like clockwork. Third, the dips are predictable. The shape of the dip is typically a smooth, U-shaped curve, as the round planet moves across the face of the round star. For years, Kepler found thousands of planets by looking for these tiny, regular, and predictable signals. It was a hugely successful method for mapping the cosmos. And then, it found KIC 8,462,852. The Kepler mission generated an almost incomprehensible amount of data, far too much for professional astronomers to analyze on their own. So they enlisted the public for help through a citizen science project called Planet Hunters. Volunteers from around the world could log on, look at light curves from distant stars, and flag anything that looked interesting. It was through this project that the strange star first came to light. The volunteers began tagging it, noting that its light curve was bizarre, unlike anything else they had seen. Their findings eventually made their way to a team of professional astronomers led by Dr. Tabitha Boyajian. When she and her team looked at the data, they understood the confusion. The star, which would eventually be nicknamed Tabby's star in her honor, was breaking all the rules of planetary transits. The dips in its brightness were not tiny. They were monumental. The first major dimming event showed a drop in brightness of 15%. Another showed a staggering drop of 22%. To put that in perspective, to block 22% of a star's light, you would need an object 1,000 times larger in area than the planet Jupiter. No planet could do that. The second problem was the timing. The dimming events were not regular. It occurred at random intervals. There were long stretches of nothing, then a series of chaotic, jagged dips, lasting for days or even weeks, then silence again. This wasn't the neat periodic signal of an orbiting planet. It was the signature of something huge, complex, and utterly chaotic. The initial reaction from the scientific team was simple disbelief. The data had to be wrong. It had to be a glitch in the telescope, a problem with the data processing, or some other mundane error. They spent a year trying to prove it was a mistake, but every test they ran confirmed that the signal was real. The star was truly physically dimming in this impossible way. With instrumental error ruled out, the team turned to natural explanations. The problem was, none of them fit. Could it be a giant planet surrounded by a colossal ring system, far larger than Saturn's? Perhaps, but even a giant set of rings couldn't account for the sheer depth and irregularity of the dips. Could it be a swarm of planets all orbiting the star? The gravitational chaos of such a system would be unstable, and it still failed to reproduce the specific pattern of the light curve. The most plausible natural idea was a planetary catastrophe. Perhaps two planets had collided, shattering into a massive cloud of dust and debris. that was now orbiting the star. This could explain the large, irregular shape. But this theory had a fatal flaw. A cloud of dust that close to a star should be heated up, causing it to glow brightly in infrared light. When astronomers pointed infrared telescopes at Tabby's star, they found nothing. There was no excess infrared glow. Whatever was blocking the light was not hot, it was cold. One by one, every conventional explanation failed. The star itself was a stable, mature F-type star, slightly larger and hotter than our Sun. With no inherent variability that could explain the dimming, we're left with a perfect mystery. A huge amount of cold, opaque material orbiting a star in a chaotic, non-periodic fashion. With all natural avenues exhausted, one astronomer, Jason Wright, put forward a hypothesis that would catapult the star to global fame. He argued that, while it was extremely unlikely, the pattern of dimming was consistent with something that could, in theory, exist: an alien megastructure. He wasn't claiming it was aliens. He was simply pointing out that after ruling out all the plausible natural theories, this unnatural one had to remain on the table as a last resort hypothesis. The idea was rooted in the concept of a Dyson swarm. An incredibly advanced civilization, he argued, might require more energy than their home planet could provide. To solve this, they could begin building enormous structures in orbit around their star-massive solar collectors to capture its energy. A swarm of such structures would be huge, irregularly shaped, and would block the starlight in a complex and chaotic way as it orbited. It fit the bizarre data perfectly. The suggestion caused a media firestorm. Tabby's star became known around the world as the alien megastructure star. Private institutions funded observation-time 2-point radio telescopes at the star, listening for any signals that might betray an intelligent source. They found only silence. As the years have gone on, the alien hypothesis, while tantalizing, has faded. The scientific community has settled on a leading, though still not definitively proven, natural explanation: a massive swarm of exocomets. The theory suggests that perhaps a passing star gravitationally disturbed a vast cloud of comets in the outer regions of the system, sending a huge number of them hurtling towards their parent star. As these comets get close to the star's heat, they would sublimate and break apart, creating a vast, clumpy, and irregular train of dust, gas, and ice. This could explain the deep, chaotic dips in brightness, and because the dust is spread out over a huge area, it would remain cold, explaining the lack of an infrared glow. While the exocomet theory is the most plausible explanation we have, it isn't a perfect fit. Some long-term dimming trends of the star still defy easy explanation. Tabby's star remains one of the most profound and alluring mysteries in the sky. It was a case that forced astronomers to think outside the box, to confront the limits of their knowledge, and to cautiously entertain ideas once relegated to science fiction. It proved that the universe is still full of impossible things, waiting in the darkness to be found.